All right, last topic for fluids is buoyancy. And so, as most of you know about Archimedes' principle, which states that the an object that's immersed in a fluid, whether it be totally immersed or partially immersed, um, is buoyed up by a force equal to the weight of the fluid displaced by the object. So, however much fluid, right, your object takes up is essentially the force that's pushing back on the object vertically. So, this is a vertical force. So um, we can think of first just drawing, maybe some water as usual. And let's say we've got some basketball that's, in the water, completely submerged, and it has some volume, right? And it has a buoyant force acting on it that is essentially equal to the volume of water that basketball, so the volume of the basketball itself, that's been displaced by its presence. So it has, right, there's some weight of fluid, so rho GV uh, in magnitude would be W, that's equal, right? And the buoyant force that the basketball actually sees is equal to that fluid that's been displaced. So these two would be equal. So that's F buoyant. So to calculate B, spelling this word is weird, Buoyant. So we know that the buoyant force, right, that's like the same force that's keeping a ship up, right, for example, um, is just the volume times the density times gravity, right? So we can kind of think of, here's my big boat in the water, same thing, even if it's just some partial amount of it, whatever amount here, in this case, this much fluid, right? This would be the weight of the fluid that the ship is displacing. That is equal to then, that's the buoyant force acting here. Now, why is it only up and down? Well, if you think about, let's just make a block. And remember what's happening. That's not to say there isn't pressure on all the sides, but in the case of the sides of the object, right, and the front and back in this case, we have a pressure gradient that looks like this, right? And it's increasing as you go down. That's certainly true. But it's equal and opposite on all sides, right? So you have the exact same pressure gradient happening over here. And so these two sets of forces, right, are going to cancel each other. However, and that would also be true on the front and the back side, which I'm not going to draw for clarity. Of course, here I have this pressure gradient or pressure level, right, which is a constant acting on the top, right, because we're at the same depth. But underneath, I have a little bit more because I'm a little bit farther down. So I'll exaggerate that. So you can see that here, the top one and the bottom one do not balance, right? And the difference between the two is exactly equal to the weight of the water that is displaced by the object. So again, the W for here is just, of course, mass times gravity, which would be density of the fluid displaced times gravity times the volume of the object, and that's equal to the net buoyant force. So let's do an application. So here we'll consider a rectangular block of wood with some cross-sectional area A, height h, and mass m placed in some body of water. And the question asks how far below the surface z is the bottom of the block, right? So we're here, right? This is the ground. And now we've got our plank of wood. I'm just going to draw it in cross section, and it's floating, right, in the water. And so the height that they're asking for is this difference, right? This is z. The whole thing has a height of h, right here. And let's say it has some base b. So h times b equals a, the area here. All right, so how do we solve this? Well, let's think about what's going on, what's happening in terms of the block of wood. So if we draw a free body diagram, create a coordinate system as always. Basically what's happening is you have the weight of the block, and this is being balanced by some buoyant force, F. B-U-O-Y. right? So let's calculate what those are, because if this thing is in equilibrium, if it's just sitting there, right, then those two forces must be balancing each other. So the buoyant force is equal to the weight of the water that's been displaced, right, which is Z, right, times B times the depth, right, which we're given, I guess, as W into the board, or the width, sorry, right? So the weight of the water is equal to rho of water times gravity times the volume that's been displaced. So the volume of the wood, which in this case would be equal to rho H2O, G, the Z, the B, and then the W, right, which we're given here in the diagram, the width of the board. And now the weight of the block itself, of course, is equal to rho of the block, so not the water, times G times B, the base, times the full height times the width. And so now we can go ahead and set up our equation of equilibrium. We know if this thing is not sinking, not moving, then we have minus W the block plus F of the buoy. Buoyant force must equal 0. So these will equal each other. W block equals F buoy. And now I'll just plug these in. So you have rho block GBHW equals rho water GZBW. So that's where Z is, right? And that's our goal. We have a lot of things that cancel. Gravity acts on both sides. They both have a base B. They both have the width W. So we can see already that Z is just a function of the density of the block, which hopefully makes some sense, right? That it's going to be a matter of how dense the block is versus how dense the water is, times H, the height of the block. Now, if W is greater than FB, if you actually solve this out, then what happens? Then the plank sinks. Right? It means you've overcome that buoyant force. There you go.